AI agents are hitting a computational wall. In their standard form, these systems are relatively straightforward. They take a single user request and work autonomously through a sequence of logical steps to achieve a specific goal. That baseline autonomy holds up perfectly fine for simple prompts. But when applied to long horizon tasks, workflows requiring dozens of intermediate interdependent steps, the architecture begins to fracture under the load. The underlying flaw lies in expecting one unified model to process everything. It forces a single agent to simultaneously act as the strategic planner setting the vision, the technical implementer writing the code, and the quality assurance checker reviewing the final output. Treating a large language model as a monolithic do-everything engine guarantees structural failure as task complexity scales. This chart shows the data flow of a standard architecture. The first predictable failure mode of this monolithic approach is context dilution. As the agent works, it generates a massive conversation history. Over time, the expanding noise of intermediate reasoning steps buries the signal of the original user goal. This triggers the lost in the middle phenomenon. Even if the correct instruction is technically present in the prompt, large language models statistically underweight critical context that fades out into the center of a massive context window. The second architectural failure mode is tool saturation. Granting a single agent access to a massive, unfiltered toolbox drastically increases the difficulty of tool selection. The model is far more likely to hallucinate a connection to an incorrect tool or pass invalid technical arguments to the right one. Throughout this entire process, the model burns immense compute, constantly context switching between high-level reasoning, like what is the overall strategy, and low-level execution, like which specific Python library do I load right now. Overcoming these hard scaling limits requires abandoning the monolithic model entirely and applying a classic software engineering principle, separation of concerns. We refactor the monolithic agent into a specialized multi-agent hierarchy. At the top sits the high-level agent, focusing exclusively on strategic planning. Below, middle-tier orchestrators manage intermediate processes and coordinate teams. At the base, low-level doers execute narrow objectives and report results back up. While this structure obviously mirrors a corporate organizational chart, with executives setting strategy, product managers overseeing workflow, and specialists doing the actual work, its real technical value lies in how it systematically routes data and compute. By enforcing these strict roles, the system prevents context switching. No single model is ever forced to act as both the architect and the bricklayer simultaneously. This hierarchy solves context dilution by restructuring how the system handles conversation history. Instead of a massive shared log, the high-level agent maintains the global state. When delegating, it doesn't send the entire prompt downstream. Instead, it extracts and transmits a contextual packet, a pruned, relevant slice of data necessary for the subordinate's job. If a low-level agent is tasked strictly with formatting a JSON file, a standard text-based data format, it receives the exact data to format. It does not receive, process, or even know about the underlying strategic business logic. This precise routing keeps the signal-to-noise ratio exceptionally high at the execution layer, completely eliminating the lost-in-the-middle phenomenon for the specialized doers. The multi-agent tree solves tool saturation by borrowing an IT security concept, least privilege. Execution nodes are strictly gated to a purpose-built toolbox. A security agent only accesses the vulnerability scanner. A DevOps agent only accesses the CI/CD pipeline. This strict narrowing prevents the security agent from hallucinating a command into deployment. It simply lacks permissions. Beyond accuracy, the hierarchy optimizes raw compute. Monolithic architectures force developers to incur the massive inference costs of a heavyweight model for every minor subtask. Through model routing, we deploy massive, expensive frontier models only at the top layer, reserving their parameters strictly for complex planning. Lower-level execution nodes, handling self-contained tasks, can be powered by incredibly cheap, lightweight, open-weight models. Mass modularity naturally enables parallelism, allowing multiple distinct low-level agents to execute different parts of a project simultaneously without locking up a central processor. It also builds in a recursive feedback loop. Mid-level agents act as quality gates, evaluating the output of the low-level doers and automatically triggering retries if the result contains an error. By combining precise data routing and exact model sizing, the hierarchy transforms a brute force AI interaction into a highly optimized, cost-effective distributed compute engine. But while hierarchical agents solve the limits of the monolith, they inherit all the classic dangerous failure modes of distributed systems. The single greatest point of failure in this entirely new architecture is the task decomposition at the high-level agent. Even current frontier models struggle with consistent planning. They frequently miss crucial software dependencies or overcomplicate simple processes by creating unnecessary steps. If the top node sequences a plan in the wrong order, it initiates a cascading garbage in, garbage out sequence. Every downstream agent inherently inherits that foundational mistake. Then there is the inter-agent communication risk, which operates exactly like a corporate game of telephone. If the orchestration logic is weak, or a contextual packet is poorly pruned, the original instruction can subtly mutate as it moves down through the layers. This communication degradation results in a frustrating paradox. The specialized execution agents at the bottom will compile and execute the completely wrong technical parameters with flawless precision. Finally, there is the massive burden of orchestration overhead. Developers are no longer just prompting an AI. They must architect the intricate glue between these nodes, designing precise state management, defining rigid handoff logic, and building functional retry loops. If that orchestration logic is brittle, agents can easily fall into infinite recursive loops. They will continuously pass the exact same error back and forth, failing to resolve the issue until the system exhausts its token limit, the absolute maximum data allowance for the operation. Multi-agent hierarchies successfully prevent an AI from getting lost in the middle of a massive prompt, but they also create the very real, brand new risk of the AI getting lost in the org chart. Hierarchical AI is not a magic fix for intelligence. It is a complex software architecture that demands rigorous validation, precisely engineered handoffs, and the baseline assumption that the high-level planner is never infallible.